Okay, so Introduction to Integration, 5.1. Right. So we, those of you who are here on Wednesday, I'm going to quickly go over some things that those who weren't here will need. So the idea, right, is that we're trying, roughly speaking, the idea is this: we're trying to find the area under a curve. Trying to find the area under a curve, and the calculus approach is always to do something simple and then take the limit of that simple thing. Okay. So you say, okay, if you gave this problem to an elementary school student, then they would say, well, I have no idea how to find the area under that curve, but I do know how to find the area of rectangles. Right? I did learn that recently, how to find the area of rectangles. So what I'm going to do is I'm going to take a bunch of rectangles. Here's one. Maybe I'll do it this way. Here's another, and here's another. Okay. That I know how to do. Right? And if the elementary student is Isaac Newton, then you say, well, and I know how to take a limit. So, if I know how to take the area of rectangles because it's just the base times the height. I'm gonna do that, but I'm gonna take the second time I'm gonna do that. I'm gonna take rectangles with smaller bases. Okay. I'm gonna take rectangles with smaller bases. Right. Do this again. Okay, so then I'm going to do the same thing, but with rectangles with finer bases. And then what I'm going to do is take right, and that will give me another area which is wrong, right? Which is wrong, but maybe a little bit better than the first one. And then I'm going to take the limit, right? Take the limit as the area of the bases gets smaller and smaller, right? And maybe that's how I'm going to figure out what the area under the curve is. So I said this on Wednesday. The motto of calculus is to analyze the unknown as the limit of the known. Right? That you take a very simple idea, right? The area of a rectangle, and you combine it with the idea of limit. And that allows you to do things that you were unable to do before. Okay, so that's roughly the idea. And then on Wednesday, we also introduced something called summation notation. Summation notation is a way of abbreviating gigantic sums. Right? If you have some sequence A1 plus A2 plus A100, you don't want to have to write that all the time, so you abbreviate that instead as the sum of AI from I equals 1 to 100. Okay. This big thing here is a sigma, capital sigma. It's a Greek letter S, right, for sum. Okay. Okay. And this thing here, the I, is the index. It's called the dummy index, right? The dummy index. Right? You can use any letter for that, right? If I say summation of from n equals 5 to 7 of bn, right? That would be b5 plus b6 plus b7, right? Right. That's how you read this notation, right? The sum of the b sub n's from n equals 5 to 7, right? If I say the sum of n from n equals 1 to 3, well, that's going to be 1 plus 2 plus 3. So you can also use, you can also, instead of putting a sequence in here, you can use, some function of n, right? If I say the sum of sine pi n over 2 from n equals 0 to 3, right? That would be sine of 0 plus sine of pi over 2 plus sine of 2 pi over 2 plus sine of 3 pi over 2. Right. Is everybody getting a understanding of this notation? Anyone confused by this notation? Okay. Then there's a bunch of famous formulas. I feel like the eraser just puts more chalk on the board. It's like an anti-eraser. Okay. There's some famous formulas. The sum of numbers from the sum of numbers from I equals 1 to n. Right, so that's 1 plus 2 plus 3 plus up to n. Does anybody who wasn't here on Wednesday know the formula for this? Have any of you seen this formula? If I add 1 through 100, or if I'm adding 1 through 77, or 1 through 10, there's a formula for it. Anybody know it? It turns out to be n plus 1 over 2. Right. So if you wanted to sum the numbers from 1 to 77, you don't have to add 1 plus 2 plus 3 plus 4 plus 5 plus 6 7 up to 77, but you just take 77 times 78 over 2. Right. You get 3003. It's a nice number. Okay, so this is one formula, right? The sum of numbers from 1 to whatever. There's also another formula, the sum of squares, I from 1 to n. This one I never remember, but it's n plus 1, 2n plus 1 over 6. Okay. We're actually going to use these formulas, so useful. A couple things to notice about sigma notation. If I have something like this, the sum of a number, so 5, from I equals 1 to 3, that's actually going to stand for your sequence is constant, right? Your sequence is just the number 5. So 5 plus, so the sum here is just going to be 5 plus 5 plus 5. Okay. Some people get confused by that, but I hope it makes sense, right? Your index ranges from 1 to 3. I is 1, I add on 5. I is 2, I add on 5. I is 3, I add on 5. This 5 doesn't change with the I. Is that clear? Right? If you're summing a constant, then you're just going to get the number of elements in your sequence times the constant, like 15. Another thing that you notice is that if I have some constant times the sequence, and from 1 to 100, say, what am I going to say? If you're summing a sequence and you sum 5 times the sequence, what do you get?
5 times 5n times n plus 1 over
2. No. So think like this. This is going to be 5a1 plus 5a2 plus 5a100. Right. So you could rewrite this. What am I going to say here, Kayla?
It's like 5 times the sum of just the variable.
The sum of the sequence.
The sequence.
Yeah. So you can pull. The thing is, you can pull the constant down. That's all we're saying. You get 5 times the sum. Right. If I'm summing some constant times a sequence, well, that's just going to be the constant times the sum of the sequence. Right. Right. This just if you have a sum and everything is multiplied by 2, then it's 2 times the sum. Right. So just an observation to make about the behavior, about the notation. And another thing I want to observe is that if I have a sum of something like this, right? If I'm summing something that's a sum of sequences, well, that's the same thing. It's going to be the same thing as the sum of the first sequence plus the sum of the second sequence. Right? You can split it up. So nothing fancy. So sum of some constant times a sequence. It's going to be that constant times the sum of the sequence. So there are two properties that we're going to use. Okay. That you can pull constants out, and that you can break up sums. Right? That's you can split this into 2 parts. Do these make sense? I hope these make sense. This is just what you know about arithmetic, right? Okay. So right now we're going to head towards defining the area. So defining the area under a curve. And what we're going to use is something called the right endpoint approximation. The right endpoint approximation. Okay. So I'll just do an example first before I give the definition, because the definition is a little bit like abstract, but it's really describing something very simple. Okay, so here we go. Okay, so somebody says, what's the area under this function? Somebody says, here's the function f of x equals x. Here's the graph of the function. I'd like you to find the area, between 0 and 5 under this graph. Okay. And you're an elementary school student, and for some reason you don't think to double it and use your formula for the rectangle. Instead, you say, I'm going to use rectangles as my approximations. Okay. So, and you do this. You say, okay, 3, 4, 5. So 1, 2, 3, 4, 5. I'm going to divide this space into, rather perversely, you insist on using rectangles. And so you say, okay, I'm going to do it like this. I'm going to divide my base into 5 pieces, and then I'm going to divide my base into 5 subintervals. And then for each subinterval, I'm going to look at the right endpoint. So there are these intervals, 0 to 1, 1 to 2, 2 to 3, 3 to 4, 4 to 5. Each one, I'm going to look at the right endpoint, and I'm going to see what the value of my function is there. Okay, so I'm going to take f at 1, and I'm going to multiply that by the width of the base, right? So the width of the base is 1 minus 0, right? And that'll give me the area of this piece here, and I'm going to do that for every interval. Okay, I'm going to do that for every interval. So I'm going to look at the second interval and say, okay, I'm going to look at the right endpoint and see how high it goes, right? F of 2 times the width of the base, that's 2 minus 1, again, 2 minus 1, right? I do it for F3, right? So add on F3 plus 3 minus 2 plus F4, and 4 minus 3 plus F5, 5 minus 4. Okay. So okay. So that would be this is what we would call the 5th right endpoint approximation. Okay. The 5th right endpoint approximation, because we've divided the base into 5 pieces. If I wanted the 10th right endpoint approximation, what would that be? Well, you divide this thing into 10, you do the same sort of thing. You divide it into 10 pieces, right? Actually, take a minute and write it down, or write down part of it or something. Write down the first few terms and the last few terms. So if you don't mind, just write down the whole thing. It'll take you a minute. Okay, turn to somebody nearby and say, this is what it looks like. Okay. Okay, would somebody like to say? Julia?
F of 0.5 times.
F of 0.5 times.
1/2 minus 0.
Okay, so times a half, say. I'm just going to, instead of writing down the, yeah, so, and then?
F1 times that.
Mhm.
And then, yeah, okay, F of 1.5
Uh-huh.
times a half. F of 2.
So just keep on going until what?
F of 10
Uh-huh. Over
times
2.
a half.
10 halves, right? Right. Okay, so that's the 10th right endpoint approximation, right? And you see that it's kind of a pain to write down. Who can express this using summation notation? Let's express this using summation notation. What's it going to be? The sum of, well, they're going to be, try it. So take 30 seconds or so and see if you can write this down using summation. Right, this is a sum. Right, let's express it using the summation notation. Okay, talk to somebody. Okay. Okay, who would like to say? Anybody like to say? Kayla?
I don't know if I'm right, but 1/2 n.
Are you summing from, is n your dummy index? N is your index?
No. Wait a second. No, yeah, n is made that
Okay.
equals a half. And then the top part is 10 halves.
Okay, so usually one doesn't use, usually one uses integers in the index. So this would go from 1 to 10, say, rather than 1/2 to 10 halves, because if you say that, then I don't know what you're using as your step, right? What's your step? Is it a half? Is it a quarter? Is it, right? So usually one uses, almost always one uses integral values for the index. Julia.
Would be 1/2 times f of n over 2.
N over 2, yeah, great. Right, the sum of f of n over 2 times 1/2 as n goes from 1 to 10. That's exactly what you have here. Okay. Isaac?
Could you rewrite that as 1/2 sigma n to the 1, 10 f n over 2?
So just move this guy over, move this guy
Yeah.
out. Yeah, that would also be fine. Yeah, because as we said before, you can pull out the constants. Okay. Okay. Right. And if we had done this one, right, this one would have been summation from n equals 1 to 5 f of n times 1, right? f1 times 1, f2 times 1, f3 times 1, f4 times 1, f5 times 1, right? Okay. Now, suppose suppose we're going from say from 5 to 10. Okay, we're going from 5 to 10. And we're dividing this thing into seven pieces, so seven parts. Okay. Then what's your? Okay, everybody take 1 minute or 2, and see if you can write down the sum for this. And so again, f of x is equal to x. But now we're going from 5 to 10, not from 0 to 5, but from 5 to 10, and we're dividing it into seven parts. So I want what's the seventh? I want the seventh. Right endpoint approximation. Actually, let's do it together. So there's going to be 7 pieces, 1, 2, 3, 4, 5, 6, 7, right? And we're going to evaluate it at this right endpoint here, right? So what is that? What is that point? We're going to have f of, let's just call this as x1, x2, through x7. What's x1? It's going to be f of, what's that point? You know what that point is, right? What's the length of the interval? 5/7, right? Because the whole length is 5, and you divide it into 7 parts. Right? So the length of the interval is 5/7. So what's this point here? 5 and 5/7, right? So 5 and 5/7 times the width of the interval. What's the width of the interval? 5/7, right? Right. And the next point is going to be what? F of, what's this? What's x2?
5 plus 10 sevenths.
Plus 10/7, right? So f of 5 plus 10/7 times 5/7. And so on and so forth, right? Up to 5 plus 7 times 5/7 times 5/7. because this will happen 7 times. Right? 1, 2, 3, 4, 5, 6, 7. Right, so the summation notation would be sum of the left endpoint plus some index times the width of the interval times the width of the interval as I ranges from 1 to 7. Okay. Okay. Everyone all right? Okay. So now I'm going to give the definition of the right endpoint approximation. Now it's going to be less mysterious, I hope. Okay, so here's how you do it. So you have, somebody gives you a function on A, comma B. You have the graph here, and we're going to define the right endpoint approximation. Here's how you construct it. You divide AB. So what I'm going to talk about is the nth right endpoint approximation. Okay? Dividing it into n pieces. Divide this thing into n subintervals. Of equal length. The length we're going to call delta x. Delta x is going to be, of course, the length of the interval divided by n. Right? It's going to be b minus a divided into n. Okay. So you divide this thing into n pieces, right? And let's call, again, let's call these points x0, x1, x2, up to xn. So A is x0, B is xn, and then you've got these guys in between, x1, x2, blah, blah, blah. Okay. We call, observe that xi is the leftmost point, A, plus I times b minus a over n. Right? I times delta x. Right? It's the left point plus some number of lengths. We call, so j, this one to n. We call this collection of points the uniform partition, of order n. I should say of AB. So uniform partition of order n. You've partitioned the interval into equal, right, guys of uniform width. Yep.
What's J?
Sorry, that should be an I. Xi is, so like x, what's x0? X0 is a plus 0 of these things. X1 is a plus 1 delta x. X2 is a plus 2 delta x's. X3 is a plus 3 delta x's, and so on and so forth.
Wait, why do you have I equals 0? Or you're just saying as I goes from 0 to n?
That's right, that's right. That's what that notation means. As I goes from 0 to n. Thank you.
What does it say? The uniform?
The uniform partition of order n. Uniform meaning that they're all the same size. Right? They're uniformly, they have a uniform length. Okay. So then, going to write it down here. We call the sum f x of j, as j goes from 1 to n, sum x of j delta x, the nth right endpoint approximation. Right, so it's the sum of all the areas that you get from evaluating the function at the right endpoint and then multiplying by the width of the base. So it's this, after you've divided this thing into n pieces. Right. So this is just a number. Right? This is a number that you get, and here's how you get the number. You divide the thing into n pieces, evaluate it at the right endpoints, and then multiply it by the widths of the base, add those things together. That's the nth right endpoint approximation. Anyone lost? Anyone confused? Anyone confused? Okay. So now we're going to define area. Once we have this thing, we can define area. So so definition, given a function f on AB, we define the area under the curve. So let's say it's a positive function, or at least non-negative. We define the area under the graph of f as the limit of the nth right endpoint approximations as n goes to infinity. So this is how we're going to define area. It's the limit of the nth right endpoint approximations. Okay. So if somebody says, what's the area? What's the area under this line here? You say, well, I'm afraid. Let me not be so perverse. Somebody says, what's the area under the graph of this function? You say, well, the way we define area is the limit of the right endpoint approximations. So what I have to do is divide this thing into 3 pieces, into 4 pieces, into 5 pieces, into 6 pieces, and so on and so forth, and take the right endpoint approximations over each of those things and see what happens as n goes to infinity. Okay. If that thing tends towards a number, then we call that thing the area. So that's how we find the area, by taking finer and finer partitions and taking the right endpoint approximations based on those partitions and see what the limit is as n goes to infinity. Okay, that's the area. So so that may seem kind of strange, right? But that's how we're going to do it. Let me do a simple example before a slightly more complicated example. Okay. So here's one that you could do by other methods, but we're just going to do it this way. So here's the example. So you have, say, the function, we're going to go from 0 to 6, and the function is f of x is 2x. And somebody asks you for the area under that. You know what it is. You know how to get it using your elementary school knowledge, but we're going to do it using the calculus way as a simple example. Okay. So you say, okay, to get the area, what I'm going to have to do is take right endpoint approximations. So the nth right endpoint approximation, well, that means I'm going to take f of 0 plus 6 divided by n times I, right? As I goes from 1 to n, times the width of each base, which is 6 over n. Everybody see that, right? You've taken the left endpoint, added on a certain number of widths, right? As the widths range from 1 to n, and you multiply by you take the function and value it at that point, and you multiply it by the width of the base, right? It's just what we had before. Okay. So now let's evaluate it. Okay. Our function, remember, is so. First off, I don't need this 0, right? Let me just cross off this 0. 0 plus anything, still that number, of course, right? So I've got f of 6i over n. My function says multiply by 2, so that's going to be the sum of 2 6i's over n, right, times 6 over n, as I ranges from 1 to n. Right? Okay. Everyone okay? Okay. So now remember, right, I've got this right, 72, right, let me rewrite this. This is summation 72 over n squared I, as I goes from 1 to n. Right? Now, this 72 over n squared doesn't change with the I, right? As I changes, these guys are constant, right? That n, it's an unknown, right? It's a number, but it doesn't change with I, right? It doesn't depend on I, right? So I'm going to pull that out. Okay, it's 72 over n squared, summation of I from 1 to n. Okay, remember I can pull the constants out. What am I going to do next? I've got the sum of I from I equals 1 to n. I'm going to use the formula, right? n plus 1 over 2, right? So this gives me 72 over n squared and n plus 1 over 2, right? In other words, 36 and n plus 1 over n squared. Okay, so that's the right endpoint approximation, right? So now what do? We take the limit. The area is the limit as n goes to infinity of this thing, 36 and n plus 1 over n squared. Right? What's that limit? Right? There was actually a meaning to us doing all those limits earlier. There's a point to it. 36, right? Because the main thing that's going to matter on the top is the n squared. You've got n squared plus n over n squared. That's as n goes to infinity, that's just going to be 1. Okay? So you end up with 36. which is good, right? Because as you know, the height is 1/2 base times height, which is 36. So you get something that agrees with your elementary school knowledge. Okay. Any questions about that? We'll do another example. Okay. So here's another example. You have the x squared function from 2 to 6. Okay, so somebody wants the area here. Okay. Yeah.
I just have one question.
Yes,
For you. How
yes.
did we get that the 12 is where we're going to?
And it's the 2x function,
Oh,
and we're
okay.
going from
We
0
can
to 6.
find the interval.
Yeah, we're going from 0 to 6.
Got it.
So that's going to be 12. Okay, so now, harder one. This you couldn't do using your elementary school knowledge, unless you combined it with the notion of limit. You say, okay, well, I want the nth right endpoint approximation. Nth right endpoint approximation. Again, so what's that going to be? That's going to be summation f at, I'd make you do it, but I think we ran out of time. Think about it for 15 seconds. What should I write down here? And then I'm just going to write it up.
And you want to come 2 to 6?
From 2 to 6, yeah. You divide that thing into n pieces. Okay. So you take the left endpoint and you add on some multiple, what are they, j times the width of the interval, which is 4 over n1. Right? And then multiply by the width of the interval, 4 over n. Right, as j goes from 1 to n. Okay. Again, now we know what our function is. Our function is the squaring function. So f of this thing is just the square of this thing, right? So you get summation j equals 1 to n of the square of that, right? That's going to be 4 plus 16j over n plus 16j squared over n squared. Times 4 over n. Right? So what do you get? You get summation j equals 1 to n of 16 over n plus 64j over n squared plus 64j squared over n cubed. Okay. Again, we can, right, so let me break this up into pieces. 16 over n, j from 1 to n, plus, I'm going to break it up into 3 separate sums. Right, 64 over n squared j, plus 64 over n cubed j squared. Is separating the sum of the 3 sequences into the sums of the sums of the sums of the sequences. Okay, and now let's look at each one. Okay. I've got 16 over n, and I sum it n times. Right. So this plus itself n times. That's just going to give me 16, right? 16 over n times is 16. I've got 64 over n squared times the sum of j from j equals 1 to n. Right? So that's good. Again, we're going to use that formula. I pull out the constant, I get the sum of j from 1 to n. Right? So I get n plus 1 over 2. Right? Here, I've got the 64 over n cubed. I've got this thing. What was the formula? It was, forgot it. n plus 1, and n plus 1, 2n plus 1 over 6. Over 6. Okay. And you end up with, if you, then take the limit as n goes to infinity. You work it out, and you end up with 208 over 3. And so that's the area under it. Sorry, let me give the punchline first. Okay, sorry, erase what I needed. 2, 6. Okay. Now here's something that will seem sort of miraculous, that should seem really miraculous. Somebody give me an antiderivative of x squared. X cubed over 3. Take any antiderivative of the function. Now look, this guy evaluated at 6, and subtract off the same guy evaluated at 2. And what you get is 216 over 3 minus 8 over 3. That's 208 over 3. Okay. That's not a coincidence that the area under the curve turns out to be the difference of the antiderivatives at the endpoints. That's what we'll see is the fundamental theorem of